Hello guys, welcome back to a brand new video. Today we're going to be doing atomic structure and electronic structure of atoms. Before I start the video, make sure you check our channel for more videos like these, and make sure you like and subscribe and comment down below if you need any help in this topic. And yeah, we're doing Leaving Cert chemistry, atomic structure and electronic structure of atoms. So yeah, let's begin. Atomic number and mass number. Atomic number of protons in a nucleus of an atom. Mass number, total number of protons and neutrons in an atom. Example, carbon 12 has atomic number of 6 and a mass number of 12. This will be already given in the log tables, in the periodic table. It will already be shown in the periodic table on the day of the exam, so it's fine. You don't have to learn this off. It will be given to you on the log table, I'm pretty sure. And the carbon shows that the atomic number is 6 and the mass number is 12. It determines the identity and isotopic form of an element. Really important. Isotopes explained. Isotopes are atoms of the same element with the same number of protons but different number of neutrons. So they have the same number of protons but different number of neutrons. Example, hydrogen isotopes have same number of protons, but hydrogen and protium have same number of protons but different number of neutrons. So yeah, and same way carbon isotopes have the same number of protons but different numbers of neutrons. So the relative atomic mass, AR. AR is the average mass of an atom of an element compared to 1/12 the mass of a A12C atom. 12C scales sets carbon 12 to exactly 12 units. It accounts for isotopic abundance. So the average mass of an atom of an element is compared to 1/12 of a mass of a A12 atom. Really important. So it just shows that it's compared to a 12th of the mass of the AC atom, and it accounts for isotopic abundance. Calculating relative atomic mass. The formula is AR equals isotopic mass multiplied by abundance divided by 100. Chlorine has two main types of isotopes. This formula, AR equals isotopic mass times abundance divided by 100, is really important for calculating a relative atomic mass. Chlorine has two main isotopes, really important, Cl 75% and Cl 25%, and we're going to be doing this on using the formula right here. So we have 35 Cl for Cl 35 multiplied by 75 plus 37 multiplied by 25 divided by 100 equals 35.5 is the relative atomic mass of chlorine's two main isotopes. The mass spectrometer. Mass spectrometer is a device that used to determine relative atomic masses. Also detects isotopes and molecular mass. Consists of several stages to analyze atoms. A device used to determine relative atomic mass. Really important. The mass spectrometer. Process in a spectrometer. Vaporization. Simple is turned into gas. So just when liquid is turned into gas, basically. And ionization. Atoms are bombarded with electron to form positive ions. So when negative atoms are turned into positive ions. Acceleration. Ions are accelerated using electric fields. And separation. Ions deflect based on mass to charge ratio. Detectation is detector records abundance and mass. Energy levels in atoms. Electrons occupy fixed energy levels shells. Lower levels are closer to the nucleus and filled first. Electrons occupy fixed energy, so they don't change. They don't change their shell if more electrons try to join, but they don't change their shape. They just stay the same. They don't get any added on, and they don't get any. They don't lose any atoms. Lower levels are closer to nucleus and filled first. Each level can hold a specific number of electrons. 2 and 2 rule. Really important. Energy increases as level go further from nucleus. Ionization of electrons. Z equals 1 minus 20. Electrons fill energy levels in order. First up to 2 electrons, second up to 8 electrons, and third up to 8 electrons. Fourth starts with calcium. Z equals to 20. Example, Z equals to 12. Mg 282. So this is how you basically draw the atom structure of an element. So for example, we can see that Mg can go into two dot circles at the start in a circle, and then 8 circles, and then two circles. So the organization of electron, Z equals to 120. Classification based on outer electrons. Elements are grouped by numbers of valence outer electrons. Group 1. 1 outer electron. Example Na. Group 2. 2 outer electrons. Example magnesium. Group 17. 7 outer electrons. Chlorine. Group 18. 8 outer electrons. Example Ne noble gases. So these groups will be judged on the places where the elements in the periodic table are. So for example, Na is in group 1 and Mg is in group 2, and in group 17 chlorine is. So everything related in that part of section will be considered to be into either group 1, group 2, group 17, or group 18. Emission and absorption spectra. Atoms absorb energy when electrons move between levels. Really important. So they absorb energy when electrons move between levels. Emission. Electrons fall to the lower energy level, releasing light. Absorption. Electrons absorb light to move to higher level. Balmer series. Visible lines from hydrogen emission spectrum. Line spectra as evidence. Line spectra shows specific energy changes in an atom. Each element has a unique spectrum, provides proof for quantified energy levels in atom used in identifying elements. Spectroscopy. So line spectra shows specific energy changes in atoms. So the changes that occur when the line spectra shows us that the changing in the atoms, and it also shows us the evidence of how the element's unique spectrum and provides proof for quantified energy levels in an atom. Energy sublevels and orbitals. Each main level N has a sublevel SPDF. Orbitals are regions with high probability of finding electrons. Shapes S orbital spherical and P orbital dumbbell shaped. Sub-level order 1s to 2s to 2p to 3s to 3p to 4s to 3d and to 4p. So each main level has a sub-level. So SPDF basically, and they have their own region with high probability of finding an electron shape. Really important. Heisenberg and wave nature of electrons. Heisenberg uncertainty principle. Can't know both position and velocity of an electron exactly. This is really important. If they ask in the Leaving Cert, in the question, if they ask, a question could be come up. What did Heisenberg do to the study of atoms? We could say that he stated that we don't know the position. We can't know both position and velocity of an electron exactly. Electrons behave as both particles and waves. Electrons could electron cloud models replaces fixed orbital models. Really important about the Heisenberg and wave nature of electrons. Fixed, which helps replaces fixed orbit model. Electronic configurations. This is the calculation bit. Electrons fill lowest energy orbitals first. AU principle. First 36 elements follow standard filling order. Ions remove or add electrons from outermost orbitals. Example, O equals 1s2, 2s2, and 2p4 is equal to O2 minus equals 1s2, 2s2, 2p6. Basically a way to balance out both sides into both parts are getting the same share of electrons, which is really important. Atomic absorption and spectroscopy. Copy. Viewing emissions spectra using spectroscopy shows line patterns. Atomic absorption spectrometry AAS measures concentration of electrons. Applications: sodium, streetlight, fireworks, and chemical analysis. So the yellow glow and the metal salts emit colors, and the chemical analysis. So there could be a question: what could the applications of atomic absorption and spectrometry cause? You could say you can make sodium streetlights, and you could do metal salt emit colors, fireworks. Really simple. And yeah, that's it. So make sure you guys check our channel for more videos like these, and make sure you comment down below for any questions, and make sure you like and subscribe, and I'll see you guys next time.